Hello, this is video number 2 about the Maxwell equations. In the previous videos number 3, we established the two Maxwell equations which are the basis of all electromagnetic theory. These two equations involved the del operator with cross product of capital E and capital B, the electric and magnetic strength. Now you are going to find the dot product of del operator with capital E and capital B. In doing this, we start from the first equation with the cross product of del and B, and we make the dot product of this equation, the left hand side and the right hand side. Now the dot product of del operator with del equals del operator cross product and B is equal to 0 according to this identity of vector analysis. Therefore, the left hand side is 0, and from the right hand side we get this expression. And if we integrate this expression, we finally have this volume integrals, and with the aid of Gauss theorem, this volume integral is transformed to this closed surface integral across the boundary surface S. Therefore, if we define the electrical charge inside the volume V as the volume integral of these expressions, then we have from above that the if we put the volume integral of epsilon times del E dV equals the total charge inside the volume, which is the volume integral of rho dV, where rho is the density charge inside the volume. Therefore, we have a third equation, del dot with E equals rho over epsilon. Now, from this third equation, if instead of del E we put the rho over epsilon, this is equal to minus 1 over epsilon del dot product of J, which is the continuity equation. Now, if we integrate this, the continuity equation, we have in the left-hand side the total charge, electrical charge, Q, the Q over dt, equals the volume integral of del J, which, with the help of Gauss theory, is a surface integral across the closed surface S, and it is the dot product of J ds. The time of evolution of charge Q, that means that inside a volume depends from what is happening on the surface. When rho equals to 0, that means there are negative and positive electrical charges. Now, the total charge Q, as we said, is the volume integral of this expression equals, with the Gauss theorem, equals to the the closed surface integral of E and ds, which is the flux through the boundary. That means this flux is equal to electric charge. Del operator with E dot E is the flux at a point, and this is equal to charge, to electrical charge at this point. Now, from the second equation, which is the cross product of del operator with E, if we make the dot product of both sides of these equations, we will get this equation, which the left hand side is equal to 0, as we said before, and therefore the left hand side is 0, which means that the del operator dot product B is constant, which means that these constants must be the 0, because when there is no magnetic field, that means B is equal to 0, then must remain constant for all times. Therefore, we have the fourth equation, which is this one. Now, in summary, we rename the Maxwell equations for mathematical reasons. The first equation is the dot product of del operator with E, and the second equation is the cross product of del equation with E, which is minus dB over dt. The same applies for the magnetism. The third equation is the dot product of B, and the fourth equation is the cross product of del equation with B. We have also the continuity equations and the force law, which is this one. Now, the flux of a vector is, by definition, this expression. That means the surface, the closed surface integral over the surface S, and with the help of Gauss theorem, this surface integral is transformed to a volume integral of del dot E, and from this we have the first of the Maxwell equation, the dot product of del and E. Now, the circulation is of a vector E around a loop is this expression, E times dl. And from Green theorem, this expression is transformed to a surface integral, not closed surface, surface integral of this vector and the dot product with ds, this pseudo vector of del and E, which is minus dt, the surface integral of B and ds, and finally we have the second equation of Maxwell. The same notion apply also for the magnetic strength B, and we have from the flux the third equation, and from the circulation the fourth equation. Now, in summary, you have the flux equal this one, and from this you have the dot product of nabla and E. The circulation is this one by definition, and from this we have the circulation of E in differential form. The same thing applies to the vector B for the flux and for the circulation. That means the flux of E through any closed surface is the net charge inside the volume of this closed surface over epsilon naught. The circulation of E around a loop is d over dt of the flux of B through the loop. The flux of B through any closed surface is equal to 0. That means there are no charges of magnetic field. The circulation of B around a loop is multiplied by C tetrago, C square is d over dt of the flux of E through the loop plus the flux of electric current through the loop divided by epsilon naught, or epsilon in general. The continuity equation is the conservation of charge, and the flux of current through any closed loop is d over dt of charge inside. Now, a quick reminder of Gauss and Green theorem. We have here a volume V and a closed surface S. The flux of this vector through the surface is, by definition, this expression, which is equal to the integral integral volume of del E, dot product E. Now, the circulation around of this loop of the vector E is, by definition, this expression. And from Green theory, we have the surface integral not of a closed surface, but about this surface that encloses this loop, of pseudo vector of del and capital E, dot product ds. Thank you very much.